Alright, so what we're going to do in this video is prove that this wacky thing right over here, which I'm not even sure what to call, let's just call it f to the f, although that name is a bit misleading because I want to make sure that clarify that this does not represent an exponent. This f on the top right does not represent an exponent, it's something completely different, but we'll talk about that. But let's just call this wacky thing to be f to the f for now because I'm not really sure what else to call it. So we want to prove that f to the f is a vector space. So first of all, what is f to the f? F is a field, which is something I'm assuming that you're already familiar with. And so f to the f is the set of all functions f from f to f. Now that was a bunch of f's. So um, let me say that once again, hopefully a bit clearly this time. And the set builder notation that I've written here, I'm not sure if this is exactly right, but this should give you an idea. What I'm talking about is the set of all possible functions between, or rather, the set of all possible functions or mappings from f to f. So if your essentially domain is f, and so is your codomain, so we can have multiple possible mappings between these two sets. One possible mapping is obviously the zero mapping, where 0 is defined to be 0 of z is equal to 0 for every single z in f. And if you want to think of this concretely, you can think of, let's say, R as the field. So we'll have 0 of x is equal to 0. And where I really want to make sure that 0 here on the left hand side denotes a function, while the 0 on the right hand side denotes the real number 0. But to avoid confusion, let's just call this function f of x. So f of x is equal to 0 for all x in R. That is an example, one example of a function from R to R. This is f as a function from R to R. Another function from R to R could be the identity function f of x is equal to x for all x in R. Similarly, that could be many possible. So every possible conceivable function that you can get between f from f to f is going to be included in your set. So yeah, that is what the set f to the f represents. We want to show that this is a vector space. So for an arbitrary vector space V, what do we need? What do we need? V alone as a set is not enough because then any set would be a vector space. Um, Not really, but essentially, a vector space isn't defined without some additional things, and those additional things are given here in this definition that I've taken from Wikipedia. We want there to be a binary operation as well as a binary function. The binary operation is what we call vector addition. The function is what we call the scalar multiplication. So a set along with these two operations is what is what is able to then constitute a vector space if it follows certain axioms. So a vector space is never a set on its own. It's a set along with two operations. One of them is an addition, one of them is a scalar multiplication. So we have, let's just write them as a triplet. So a vector space V, an addition function plus and a scalar multiplication dot. Again, to recap, I'm assuming you're familiar with what an addition is and what binary operations are in general, but um, plus is a function from V cross V, the Cartesian product of V with V, to V. So in other words, it associates to with every ordered pair UV, where U and V are both vectors in V, another third vector W, which is also in V. So that is the addition function, and the scalar multiplication function would be a similarly defined function, but it'll be defined from f, where f is a field, which the vector space is defined over. Also, by the way, you need to have one other thing in this to make it really complete. So vector space, along with a along with an addition and a scalar multiplication, along with the field which it is defined over. That is all the information that you need to then check if certain axioms are specified, uh, which will then make V a vector space. So a vector space is never alone. A set alone is not a vector space. You would need to have a set along with a field over which the vector space will be defined over, along with two operations, an addition and a scalar multiplication. So dot is a function which is defined from the Cartesian product of f with v to v. So it associates, in other words, with every single lambda in lambda in f, where lambda is a scalar, and v, where v is a vector in v, A third vector w, where w is a vector in V. Typically, by the way, and I should have mentioned this for plus as well, v and w, it and associates with u and v, a third vector w. Typically, you would not write binary operations like this. You would write them with the function in the center. So u plus v is equal to w is typically how we denote addition. And lambda dot v, or even written more succinctly, we write lambda v is equal to w. But anyway, hopefully this should all be a review to you. So we need, what do we need? We need v, the vector space with the set, sorry, which you already have. We need an addition, we need a scalar multiplication, and we need the field. For our purposes, we already have our specific case. We already have what we need for the set. The first entry, f to the f, is what you need to show as a vector space. And we have the field. The field we're considering is still a general field f. What we need are specific definitions for plus and dot. So we need a definition for the addition. We need a definition for the scalar multiplication. So the plus will need to be a function from f to the f, Cartesian product with f to the f, to f to the f. So a very typical definition that you see being used for functions is, so by the way, let me make clear what are the inputs to plus. The inputs to plus are ordered pairs where each element in the ordered pair is a function from f to f. So plus is defined on an ordered pair of functions f, g, where f and g are functions from f to f, or we can write they are functions from f to f like this. And then it associates with with this ordered pair a third function which is also in f to f, or I should say h is also a function from f to f. So you need, you want to take two functions from f to f, and with on the ordered pair of them, you want to also associate with them a third function from f to f. So the way we would typically define this is we're not going to use g. Let's just say we define f plus g from f to f, and we know this is going to be f from f to f, because remember we chose to call f plus g as h, and we know that the output of f plus g would be a function from f to f. So this is a function from f to f, and we define it as f plus g of z is equal to f of z plus g of z for every single z in f. And this definition makes sense because f plus g of z is going to, so f plus g is a function that takes in a field, a scalar as an input, and outputs again a scalar as an as an output. So it's taking for every single scalar z in f, we are mapping that scalar, f plus g rather is mapping that scalar to the scalar f of z plus g of z. Why is f of z plus g of z a scalar? Well, because f is a function from f to f, so f of z is well, f, I'll write this over here, f is a function from f to f. So f of z will be well, in f. So this is f where f of z lies. Similarly, so is g. So g of z will also lie in f. And so these are both in f. And you know what happens when you add two things in a field. You get another third element which is also in the field, because addition on a field is closed. That is something we know. So great, we know this. So this definition makes sense, and we're going to use this definition because it's quite convenient. And so this is really the definition. Strictly speaking, the problem in the problem I should have specified, I should have written here that we want to prove that f to the f is a vector space with this definition of addition and this definition of scalar multiplication. But yeah, I wanted to talk about what the definitions are in the video, because otherwise the question itself would have appeared to be long, because we would want to specify the definitions. So now that I've clarified what the definitions of addition and what scalar multiplication are, you would typically see the definitions however defined in the problem itself. But yeah, for the purposes of this video, I'm defining them right over here. So we have defined f, we know what f will be. We'll use that in the proof that this is a vector space. Finally, lambda will be defined in a very similar way. So lambda, sorry. Dot will be defined in a similar way. So again, dot is going to map f cross f to the f, sorry, cross f to the f to f to the f. So essentially it's going to take as input two functions from, no, my bad. It's going to take f, the Cartesian product of f, the field with the vector space, and to that it associates an element of the vector space. So f cross f, so it is going to take as input an ordered pair of a scalar lambda and a vector v, no, not a vector v, well, technically a vector, but a function here. uh, um, and I said technically a vector because we are going to, as we're going to soon see, f to the f is indeed a vector space. And so f, every function from f to f is technically also a vector. So anyway, but we're going to associate with every ordered pair a second function g, which is also from f to f. And so we're going to define this to be, and we're going to write this as lambda f. So we define lambda f from f is a function from f to f, which we define to be as lambda f of z is equal to, and notice that this is the function from f to f, so z is a scalar f, and the output of this function should also be a scalar, so that is going to be, we define it to be lambda times f of z. So f of z is obviously again a scalar because f is a function from f to f, and lambda is again a scalar. So a scalar multiplied by another scalar is a scalar because well, fields are closed over multiplication as well. So yeah, now that we have definitions laid out for dot and plus, now we can finally start with the proof that this is a vector space, which will involve us verifying how many properties? 1, 2, 3, 4, 5, 6, 7, 8 properties. Okay, that should be doable. Let's do that. So we want to first verify associativity of vector addition. So I'm not going to write this down as a formal proof because for the sake of time, I think I've already spent quite a lot of time in this part of the video, and we haven't even technically started with the proof yet. We were laying out all the definitions first. But anyway, associativity, let's start with that. So we want to show, our goal is to show that f plus g plus h is equal to f added to g plus h for all f, g, h, where all f, g, h are functions from f to f. And now that we already have a definition of addition, we can use that in this problem. But anyway, so let's suppose, to work towards the goal, let's suppose that f, g, h are three functions from f to f. Or you can even write this alternatively as f, g, h are functions from f to f. But I prefer writing the set notation, membership notation. Anyway, suppose there are three functions. Then we have, let's consider f plus g plus h of z is equal to, and I'm going to say for all z in f, so I don't forget it later. So just making sure that essentially I want to prove that f plus g plus h is equal to f plus g plus h. That was my goal. And the way to prove that any two functions f and g are equal, so equality on functions is defined. The two functions f and g are said to be equal if f of z is equal to g of z for all z in f. So in other words, when you consider the outputs of f and g on every single one of their inputs, if they agree on all the outputs, then they are the same function. They are the same mapping. They map the same inputs in exactly the same way, so they are the same. So to prove that these two functions are equal, we really, what we're going to prove is that their outputs are equal to each other for every single possible input. So f plus g plus h of z is equal to be, well, is equal to, well, we had the way we defined our addition function or addition operation was, we can just say this is equal to f plus g of z plus h of z. So essentially breaking or just using the definition as we defined it there. So now f plus g again is something we can break down. So this is equal to f of z plus g of z plus h of z. Notice f of z, g of z, and h of z are all scalars because they are, again, f, g, z are elements from f to f, so their outputs are scalars. So scalars on, we know that associative property is true for scalars, so we can just simply write this as f of g, z plus, choose to add g and h of z first. This becomes f of z plus g plus h of z, and this finally becomes f plus g plus h of z. And so this, since these two functions agree on all outputs, they are the same function. Therefore f plus g of h, sorry, f plus g plus h is equal to f plus g plus h. Cool. That is associativity. Let's now prove commutativity. Suppose f, g are in f to f. So there are two functions from f to f. So we have f plus g of z is equal to f of z plus g of z. I'm being a bit complacent with my writing here. It's not formal because I'm doing this in the interest of time. So yeah, you can make the proof formal. F of z plus f of z plus g of z, and again f of z and g of z are now both scalars, so we can use commutativity on scalars or on fields to make this g of z plus f of z, which is equal to g plus f of z. So we have shown that f plus g is equal to g plus f. Great. Now we're going to show identity element. So there exists an element 0 in V, which we call the 0 vector, such that V plus 0 equal. Okay. So we want to show that there exists a function in f to f such that f plus 0 is equal to f for every single f in f to the f. I hope that was at least somewhat understandable considering what a mouthful it was. But anyway, you want to show that there exists, and I'm going to use the notation 0 here. This is not to be confused with the real number 0. This is a function in f2f, and we typically use the same notation of this oval symbol here to represent the concept of an additive identity in not just the real numbers but in general in fields as well as in objects like vector spaces. So don't get confused, this 0 is a function. There exists a 0 such that f plus 0 is equal to 0 for every single f in f to the f, and I hope that makes sense. So we want to show that there exists. So if you're able to write a function which is clearly a member of f to the f, f to f, f to the f, I guess, yeah. If you're able to write a function which from f to f which satisfies this property, then we have found a function in f to f, and therefore we have shown that there exists a function in f to f, and that will be the end of that. So choose 0 defined from, or rather I should say define 0 from f to the f to f. And if you're able to make sure that this function definition is valid, then obviously this function clearly then will exist in f to the f. So let's define it as 0 of z is equal to 0 for all z in f. It's a very simple definition, but note that 0 here is a function on the left hand side. It's a function from f to f. 0 on the right hand side is a scalar. It's a member of a field. So these are two different zeros. So we have, and suppose f is a member of f to f. Now we have f plus 0 of z is equal to f of z plus 0 of z using the definition of addition on that we defined, and f of z will be a scalar, z of z will be equal to 0. So this is f of z plus 0, where 0 is a real number. Oh, sorry, not a real number, a scalar. And we know that f of z is a scalar, 0 is a scalar. So clearly, because additive identity is a thing in fields, this is the additive identity on the field, and so this is going to be equal to f of 0. So that proves that f plus 0 is equal to f as was desired. Oh, my bad, I should have written f plus 0 is equal to f. Apologies. So we've proved 3 properties so far, 5 more to go. Now we want to prove that there exists an inverse element for every single element v and v. So suppose f and f and really f to the f. Now choose define I should say. Define a function. I'm not going to call it negative f because I kind of like, at least initially when proving stuff like this, I like to use a different symbol for the inverse, something like f dash or maybe g, because negative f seems, even though it should be treated as a single symbol, it seems like a combination of two symbols to me. So I like to avoid that notation initially. Later, obviously, you're going to be using this notation almost exclusively. So we define g as a function from f to f, and as g of 0 is equal to negative of f of 0. Now I did say I'm going to avoid the use of negative, but we already are assuming that we already have properties of the fields established, which we uh, um, uh, technically they are studied more in depth in the course on abstract algebra, but here we're assuming that we have the properties of real numbers established. So we know that for every z in f, for every element z in f, there exists an element negative z. such that z plus negative z is equal to 0. So since we already have that established, I'm going to choose the symbol negative of f of z, and f of z is a scalar. So negative f of z will be that scalar, which when added to the scalar f of z makes the sum 0. So now we have f plus g of 0 is equal to f of 0 plus g of 0, and g of 0 was defined as negative f of z. 0 plus negative f of z. So if you add a number with its, and a number by number I mean a scalar which is a member of a field, if you add a number with its additive inverse, you get 0. So 0 is equal to 0 of z. So we have shown that f plus z is equal to 0 of z. So this last step might seem unnecessary, but it's really important. This 0 is a member of a field, and we want to show that this function is equal to another function. So we want to show that f plus z is equal to the function 0, not the uh, element 0, or where s 0 is a scalar. So this last step was to show that the function f of f plus g agrees in output with every on every input with the function 0 of z. Cool. 4 properties down, 4 to go. Compatibility of scalar multiplication with field multiplication. So we want to show essentially that f times g of sorry, we want to show that a times b of f is equal to ab times f for every single a b in scalars, and a b in f and f in f to the f. So we're going to suppose that a and b are two functions from f to f. Let's write them as f to f, and also that f is a function. Sorry. We're going to suppose that a and b are two scalars, and suppose that f is a function from f to f. So we have a times bf, this entire thing acting on z, the input z, for all. I should write for all z in f first, so I don't forget later. This entire thing acting on z is equal to well, we know how scalar multiplication is defined, so we can write this as a times, well, bf of z, which is equal to, again, we know how scalar multiplication is defined, so we can write this as a times b times f of z, and this is going to be equal to, now we can use the associative property on, because a, b, and f of z are all scalars, so we can write this as a b times f of z. And again, we use the definition of scalar multiplication on that we defined. So this will become AB times F, all of this acting on Z. And if you notice, A times BF is equal to AB times F, which is what was decided. So these two functions agree on every single input. 5 properties done, 3 to go. We want to show that identity, there exists an identity element in in scalar multiplication. So we are going to say, suppose, or rather, consider the function I from f to f defined by I of z is equal to, and I really apologize for the terrible handwriting. I'm kind of in a hurry because I don't want this video to be too long, because it's already stretched quite a bit now, but hopefully I'm making sense. I of 0 is equal to 0 for every single z in f. So now we say, suppose f is a function from f to f. So we say 1, or actually, yeah, I should have, maybe let's call this I, instead of calling it I, will call it 1, because to show that there exists a 1, such a 1, just like we did for the additive identity up above, such that 1 of z is equal to 0. And notice this 1 is not a scalar, not a real number, it's actually a function. I mean, it's defined like this. It's just a symbol for a function, just like f, g, h, 1 is a symbol. So we say that, oh, my bad. Did I mess it up? Oh yeah, I'm so sorry. 1 is not, I am so sorry, I messed up. I am not considering 1 to be a function. I'm not trying to multiply two functions. That is not something, you don't typically multiply two vectors, or at least you don't in you have specific ways of defining the product of two vectors, but that is not something that we talk about right now. And we only define scalar multiplication in the definition. And so we want to say that consider 1 in f. That's 1 is indeed, my apologies, 1 is indeed the element of a field. So if it was a complex numbers, this would be the number 1 plus 0 I. If it was the real numbers, it would simply be the real number 1. So yeah, consider 1 in f. And if it was any other field, it would be the multiplicative identity of that field. Is in general, it's that's what they say in the Wikipedia definition. So suppose f is a function from f to f, then 1 times f of z is equal to, by definition of scalar multiplication, is equal to 1 times f of z, which is equal to, well, this is a scalar, 1 is a scalar, 1 is a multiplicative identity on a field. So this really becomes f of z. And which, so that proves that 1f is equal to f for all z in f. Cool. That is done. Distributivity of scalar multiplication with respect to vector addition. So you want to show that we want to suppose a is in f. We want to suppose two functions f and g are in f to the f. So you want to show that a times f plus g is equal to af plus ag. We want to show that. So consider f a times f plus g of z is equal to, we're going to use the definition of scalar multiplication. This becomes a times f plus g of z. We're going to now use the definition of addition. So this becomes a times f of z plus g of z. And we know that distributive property is a thing for scalar multiplication. So for scalars, so this is a scalar, this is a scalar, this is a scalar. So this becomes a times f of z plus a times g of z. And now we know that we know the definition of scalar multiplication on that we define for this vector space. We can write this as the function af of z plus the function ag of z. Notice earlier this was the scalar a times the scalar f of z. Now it's the function af applied on uh, well z. So earlier it was the scalar a multiplied by the output of the function f on z. Now it's the function af, or we're considering this to be the output of the function af, where the acting on z. Okay, cool. So this is now equal to, again using the definition of addition, this becomes af plus ag of z. So with that we've shown that a times f plus g is equal to af plus ag for every single z in f. Last property, and I remember that basically, so I don't need to go up there. You can check. In fact, let's just check. A, B, and V, right? So we want to show that A plus B times F is equal to AF plus BF, where A, B are scalars, F is a vector, so a function from F to F basically. So suppose I'm just gonna write S. Suppose A, B are scalars, and F is a function from F to F. We say that a plus b of the function a plus b times f of z is equal to, we're going to use a definition of scalar multiplication, a plus b times f of z, and if this is equal to a and b are scalars and so is f of z. So again we use the in fact I could be more strict with this and say that the commutative property is true, and so this on multiplication, so this becomes f of z a plus b, and then you use a distributive property. But really I think that's just a roundabout way of going. We know that the distributive property works this way as well on scalars, so I'm just going to use it directly. A f of z plus b times f of z. Now this is a multiplied by the scalar f of z, and by the definition, or rather it is a multiplied by the output of the function on z, and by definition of scalar multiplication on the vector space that we defined, we can write this as a times the function f, and that is a new function which acts on z, plus b times the function f, that is a new function which acts on z, and we use the definition of addition to make this af plus bf of z. And with that, we've proved that a plus b times f is equal to af plus bf for all z in f. Okay. And by the way, I said that a plus b times f is equal to a plus bf for all z in f is that is not exactly what I mean to say. What I mean to say is that this thing is equal to this thing for all z in f, which means that a plus b times f is equal to af plus bf. So we don't say that a plus b times f is equal to af plus bf for all z in f. All we say is that two functions are equal. So we say that the function a plus b times f is equal to the function af plus bf, because we have shown that their outputs are the same for all input z and f. That's what I meant to say, just to clarify. And with that, we've proved every single property, both the distributive properties as well. So that was 8 properties. And therefore, we have the proof that is required. So we have proved in a very ugly way, I apologize for the bad handwriting, that f to the f is a vector space.